Hi everyone, my name is Martin Halaj. My supervisor is Martin Madaras, and this is my first talk ever on doctoral colloquium. So I want to give you some insight in what we do and about our topic. So first of all, I want to show you some big picture. I called today's presentation from Pixel the Person, constructing metrically accurate 3D human models. So I want to give you some big picture first, so you can see where human virtual avatars are used or what we do with them. So I selected some 4 areas I will be talking about. First is connecting people, entertainment, e-commerce and fashion, and industrial simulation. So connecting people, virtual reality, together with virtual characters or humans, changing the way we interact with other people, how we have some social interactions. I have some examples here. This is the Microsoft Mesh application, and you can see people in the picture that they have a Teams meeting inside the virtual world where they present, collaborate together, and this can be very useful for like overcoming geographical boundaries. When you have, like in this company, they see technology where they have people in team from different parts of the world. They can collaborate together in virtual space. Another example for social virtual reality is metaverse created by Meta. This one is called Horizon Worlds, where you can talk with your friends, have some fun, or play games, or even work in this space. And in both, you can somehow create your own avatar or your own character. So the next, entertainment. There is probably something you would expect. I have here a sample from Epic Games, the company that created the famous Unreal Engine. This is their tool called MetaHuman Creator, where you can design and create virtual humans. You can see a little bit word on the projector, but they have a realistic skin, hairs, and beard. So some novel use is e-commerce and fashion, where in e-commerce we have some virtual influencers, or some novelty use like virtual try-on, where in theory you have some web page with clothes. You can create a virtual model of yourself and then choose clothes from the shop and try it on and see on the model how it would look on you. So probably everyone of you see this virtual avatar. It is she's created by Renault, and it was their ambassador for their new car, I think Renault Kadjar, where they created her so she can they can use her in commercial. And the last area I selected is industrial simulation. Here we have a screenshot from Siemens Technomatics. And you can see there are also here some avatars in lower quality, but they are there and they need them. This is the software for designing working environments and creating environments so that people don't injure in the environment. So some motivation in summary. There is growing demand for lifelike avatars in video games, virtual reality, or other areas I mentioned. We have some innovative uses like virtual try-ons, and we can achieve a new level of detail, for example, by using neural networks. I will be talking about this later. But there are some also data gaps I will talk about later. So this is research vision for my PhD the whole PhD study for now, but probably it will change in the future. So the first is understanding of the building blocks, like the realistic human models, then create some frameworks that will create these human models based like on image, or if you want to create a virtual model of yourself, use some new rendering techniques I will talk about later, and in the result we want to have some photorealistic avatar generation. So this is the ultimate outcomes we want from I want to have from my thesis, that is hybrid avatar modeling, so the whole framework for creating virtual copies of people and also some evaluation. So there are some challenges in creating virtual humans, like you have to match shape and size of the modeled person to be realistic. You need some realistic skin, hair, and clothing, which is complex topic. And also you want to create avatars that are usable in existing software, because no one wants to use something that probably you cannot use, for example, like in Unity engine or Unreal. And you need to be able to control them for animations or in video games. So here is some related work I want to talk about, because I will be mentioned these models through the whole presentation. So what is skinned multi-person linear model? In short, SMPL. It is a realistic model of human body. What is important for us, that it is parametric model. So you can take some vector or array of parameters, put it in the model, and it will give you the resulting model based on these input parameters. And they are animatable, they have bones, and
what means linear in the name?
It's a bit complex. It's like how the model works under and how it processes the input parameters, because they are used like linear blend shapes that affect each other. So that's why linear. So here is the example model with highlighted skeleton with 23 joints and the polygonal mesh. So building on past research, automatic estimation of anthropometric human body measurements. It was the part of PhD thesis of Dana Škorvánkova that finishes her PhD thesis last year. And in her work, she estimates body measurements from visual data like 2D images, 3D point clouds. And we used her work in ours. You will see that in a moment. And during her thesis, she also tackled the challenge of lack of real-world data. So this is example from her work. So current state of our research. So this is the motivation, what we want to achieve in a result. At the start, we have a user. He can decide if he wants to insert the measurements of himself, like anthropometric measurements, manually, or he take the picture from front and from the side. These pictures are then processed with our tool and then converted to SMPL parameters, and we can create a model. So I will talk about the data generation, because it is part of our work. So we all know that if we want to train some great neural network, we need a lot of data. But in some areas there is not enough data, so we decided to create a synthetic ones. In some areas it can be due due to expensive capturing cost of imageries like tomography or magnetic resonance. But in our case, it is more like convincing a large number of people to participate, because if you want to have body models, you need to scan people, and many people, so it is not really easy. And also legal complexity, because if you scan people, they have some rights, and you need to protect their personal data. We have GDPR and so on. So the only dataset I know that contains these photos of real people with their body measurement is body M dataset. It contains approximately 9,000 images of 2,050 individuals. And for each participant, we have 14 body measurements. However, there are some also challenges, because the authors of this paper do not precisely specify how they get the measurements. So there is space for some bias. This is the example for dataset. As I said, due to privacy reasons, these first two images are not included in dataset. Only these silhouette photos are available together with 14 anthropometric measurements, including weight. So we want to create data generator in order to generate the synthetic data to extend existing real data set. So we used synthetic humans for action recognition from unseen viewpoints, in short, SURACT, that was designed for generating synthetic videos for action recognition tasks. So like if the person in the video drink, sits, walk, run, or etc. And in their paper, they proved that using synthetic data together with real data can be really beneficial for the final neural network model. And they also showed that neural network trained only on real data has worse performance than network trained on the combination of synthetic and real data. So we expanded the real data set with the synthetic ones. We generated over 1 million files for more than 1,000 different subjects. And for each subject, we have 12 pictures and also 16 measurements for each one. So this is the sample for our data set. We have pictures from front, from side, pictures with and without background, also 3D model, and also position of joints in 3D space. And this is all for avatars in T position and also in A position. So this is the showcase from the whole dataset, some sample, where you can see that the avatars have different texture, different background. So there are some statistics for our generated dataset. This is a graph that represents BMI for these avatars. This distribution is, in a result, is very similar to the estimated real distribution in the population. And also the distribution of height of avatar in our dataset, where there is also, it is very similar to real estimated height distribution in population. So data evaluation. When we have these synthetic avatars we generated, and we have body and dataset I talked about before, we can predict 10 anthropometric measurements, because our dataset have some measurements, a body M dataset has some other measurements, and the intersection of these measurements are the resulting 10 measurements. And for the test dataset, we use exclusively real-world data. and we tried different neural network architectures. So this was the first network we designed. As input, it takes two silhouette images with sizes with the sizes, and then they both go to ResNet 18 block where they are processed and the result is concatenate, and we have some other dense layers and the final resulting 10 anthropometric measurements that we estimated. This is results of our network. We can see some minor improvement when we added the synthetic data to training process. We tested this data only on test B. That means body and dataset has two test sets, and the B is the more challenging one where the camera angles are not consistent, etc. And after that, we think how we thought how we could improve these results. So we decided to add height as another input parameter together with photos, because many people probably you don't know what is your chest circumference, but you know probably what is your height, at least approximately. So we add it and put it to the results, and we have another layer. So these are the results for height-driven network, where we also was able to get some improvement when adding the synthetic data to training process. And this is the comparison between the base model and the height-driven model, and we see that the improvement is more than 1 centimeter for real data, and the same applies for the combination of synthetic and real data. Here is the table for each measurement we took, and that's probably only for look. So when we have the anthropometric measurements of the input images, based on them we can now take these measurements and convert them to SMPL parameters in order to create SMPL model. So we have input is body measurements, as I mentioned, and output is 10 shape parameters for SMPL model. Shape parameters for this model, they affect the visual of the model, so how high it is or how long legs it has, and so on. So we done 2 experiments. The first, we pick only some 5 basic measurements. We used like height, chest circumference, inside leg height, shoulder breadth, and waist circumference. And the second experiment, we use all 16 parameters. So this is the results for the first experiment. We was able to achieve the best results with random forest algorithm, but these are not centimeters. These are the errors that when comparing the beta parameters, so the shape parameters I mentioned before with the expected ones. And this is for the second experiment where we use all 16 available measurements that we have, and we can see that the error is almost 0 on these parameters, with a polynomial regression of 4th degree. So when we converted these anthropometric measurements to SMPL parameters, we can now create model, and for this model we can then create some simple clothes and give it some simple skin texture. We used SMPL for Blender, that is a plugin for Blender created by developers of SMPL model. And we also use the Blender's powerful cloth simulation in order to generate realistic clothing. We tried two methods. The first one was using sewing to create the clothes. However, we have some problems with scaling, and the second method, with better results, we achieved by extruding mesh of the avatar. So this is the first method. We created two planes that are then sewed on the avatar. Here are the results with some basic textures. Well, we can see some problems with sleeves, and also there was problem with scaling when the height of avatar was changed. And this is the result of second method. So we can see that the avatars and the clothes looks much better. And this is some results from the second method, where the avatars have trousers with different types of shirt. We have t-shirt, a regular shirt, and some no sleeve shirt. So the final pipeline, it has a dual input system. So as I mentioned, the user can decide if he insert the measurements manually, or he takes photos and we extract the measurements from these photos. Then we generate model based on these measurements, and finally we add some simple clothes and skin texture to resulting avatar. There is some limitation, as you probably noticed. We completely missing hair at the moment. Also, we use only the basic texture, which are not photorealistic and not corresponds to input photo. And also there are limits compared to the newer methods I will talk about later. So the good news from the last week is that this work I presented was accepted as full paper on WSCG conference. So I'm looking forward to present here during the May of this year. So some path forward, or what we will look to next after this paper. The problem with traditional meshes is that they struggle with photorealistic details like small cavities and so on, because it is computationally extensive. Also, it is difficult to capture complex, some view-dependent effects like reflection. So we have some new methods like neural radiance fields, or in short, NERFs. These represent a scene implicitly with a neural network, in this case with a multi-layer perceptron. And as input, we put there 3D point with its 3 coordinates, and also weaving directions, so 2 angles. The output is then the color emitted from that point in direction, and the density of the point, so how opaque it is. And it is, in analogy, it is like teaching a network to describe the light and the substance at every single point in volume. So training of NERF input is many images of scenes. It is something similar to photogrammetrics, but in photogrammetrics you don't have any neural network you train. So process is you cast ray from the camera through pixels into the scene and sample many points along each ray. So you can then query the MLP at each point to get the color and the density. Then we use the volume rendering math to combine these colors, or they use, because it's not my work, they use and then compare the rendered code to the actual input image, and then update MLP weights to minimize the difference loss. So the result is that the MLP learns the 3D scene structure and the appearance implicitly, because it is function. And when we want to render something, we just choose the new camera viewpoint that we don't have before. We cast rays from it, and query the trained MLP along these rays. So the result will be a photorealistic image from a viewpoint never seen during the training. So here is an image, how it looks like. We have many input images. We train NERF on them, and then we can choose some new viewing angle and render this new view. This is also the representation as I mentioned. We have 3 coordinates and 2 angles for each ray, and with sample points along these rays. So one big disadvantage of NERFs are they are slow. So Gaussian splatting is something new that aims to achieve the similar quality as NERFs, but in real time rendering speeds. So instead of implicit representation, we have explicit 3D Gaussians, and we can think of each Gaussian as a fuzzy, semi-transparent ellipsoid in 3D space. And each Gaussian has its own properties like position, shape, orientation, color, and opacity. And it is analog to is representing the scene with millions of tiny colored shapes, semi-transparent paint splats in 3D, like you would paint some small dots on the paper and create the whole image. So input are also many images plus non-camera poses. It is the same as for NERFs. And in the process of training, we want to iteratively adjust Gaussian's parameters, so render current Gaussians, compare rendered images to the ground through calculate loss and update all the Gaussian's properties I mentioned before, and periodically densify and prune. So we remove the invisible ones, so it is more optimized, and the result will be the optimized set of Gaussians creating a 3D scene. So when we want to render Gaussian splatting with this method, we project all 3D Gaussians onto 2D image plane, so they become 2D splats, and we store these splats based on depth, and in the result we get a photorealistic rendering at real-time frames. So future work, we want to combine and create a hybrid models using this technique. One new area we want to focus on is hybrid 3D animal models. So we want to, I will go to, so we have context before the slide. Very similar to SMPL model I mentioned at the beginning of the presentation, we have also parametric model for representing animals. So we decided that we start with the animals, and we want to combine this small model with new methods like Gaussian splatting and NERFs in order to create furry on these animals, fur on these animals. So for this, we want to, as a first step, we want to try to do that with NERF texture. That is implementation of NERF where you can take images of some texture you want to replicate and then apply this texture on some new objects. So another work that I also look into and will in future is that the idea we don't need ordinary or traditional human body model, but we can create this model by Gaussian splatting. So we have a new model using that, and we don't need textures or clothes from Blender. Another example of using Gaussian splatting is for creating hair. You can see this is real picture. These are highlighted hairs, and this is the final rendered model. So you can see that it is really realistic and high quality result. Or something very new that comes out this year is Tau avatar, and this is not a real person. It is model created using the Gaussian splatting by capturing the real man before. So, thank you.